Section 2.1, Relations and Functions. So a relation is a set of pairs of inputs and outputs. There are 4 ways to represent a relation. You can do so using an ordered pair, which would be your XY coordinate points. A mapping diagram where you have the inputs in one column, outputs in the other, and you map the input to its corresponding output. There's the table, and there's a graph. So in this example, it says the monthly average water temperature of the Gulf of Mexico and Key West varies during the year. In January, the average water temperature is 69 degrees. In February, it's 70 degrees. In March, it's 75. And in April, it's 78 degrees. We want to represent this relation in 4 different ways. So let's just go ahead and start with the ordered pairs. We know ordered pairs, we're representing them as X and Y coordinates. But for this case, we're going to go ahead and let X be our months, and Y is going to be our temps. And we're going to represent the months as their numerical values. So January being 1, February, March, and so on. So here we know in January, the temperature is 69 degrees. In February, it's 70. In March, it is 75. And then in April, it is 78. So here we have the representation as ordered pairs. We can also then do a mapping diagram where we have our inputs in one column and outputs in the other. And so keep in mind for our inputs, we're going to be using the months, and the outputs, we're going to be using the temperatures, or in this case, X and Y. So input-wise, we've got 1, 2, 3, and then 4. I'm going to put an oval around this. There we go. Outputs, we've got 69, 70, 75, and 78. There we go. Put an oval around this. And we're going to map where each one goes. So we know in January, maps to 69 degrees. February maps to 70. March maps to 75. And April maps to 78. Table's very similar to the ordered pairs, so this one's pretty quick. So table of values, you've got 1, 1 and then 69, 2 and then 70, 3, 75, and 4, and then 78. And the last thing we're going to talk about is representing this graphically. With the larger numbers for the output, you're going to draw a specific graph to that. So this is one possible graphical representation of what our function would look like. Depending on how you scaled your y-axis and your x-axis, it could look a little different. All right, so here we have the term domain. Domain is the set of inputs, also referred to as your x-coordinates, of your ordered pairs. Range is the set of outputs, also called the y-coordinates of the ordered pairs. And then function is a relation in which each element of the domain corresponds with exactly one element of the range. Sorry about the crazy background a second ago. This makes it a little easier to read. So domain are your inputs or your x-coordinates. Range is your outputs or your y-coordinates. And then a function is where you have each element of the domain, so each input, corresponding to exactly one element of the range. So here we want to just state the domain and range. So keep in mind, for this, we know that domain is our x values, range is generally your y values in this case, because we're dealing with x and y of ordered pairs. So for domain, we'll just list them out. So we've got -3, 0, 2, 9, and 23. For range, we're now going to list out the y values. So 14, 7, 0, -18, and -99. And that's our domain and range. We'll do the same thing in question B. We're just going to list out our domain and range values again. So domain is the x values, so we're just listing them out. -7, 9, 14, and 7. For range, we'll list these values out. 14, -7, 7, and 14. Well, notice here that 14 repeats, so we actually do not have to repeat it in our list. Since it's already here, we only list it once. So here we want to identify whether or not each relation is a function. Keep in mind, to be a function, each input must correspond to exactly one output. So domain going to one range. So for example A, we've got -3 going to -2, 0 going to 7, 4 going to 1. Each input or domain value is used once. So since every input or every domain goes to one range, this is a function. So question B, we have a very similar situation here, except it's not done in a mapping diagram, but we can still see whether or not each input or x value goes to a unique output. So here we've got 4 to -1, 8 to 6, 1 to -1, 6 to 6, and then 4 to 1. Notice here that the input of 4 is used twice, but it goes to two separate inputs. 4 is going to two separate outputs. It's going to -1 and 1, so this is not a function. Question C, same idea. We're looking at the inputs compared to the outputs. -7 goes to 14, 9 goes to -7, 14 goes to 7, 7 goes to 14. Every input is used once and it goes to an output, and so this is a function. And then question D, as we look at the domains, our inputs, we notice that there are two lines coming off of the input of 2. 2 is going to -3 and 3. Since that input does not go to exactly one output, it goes to 2. This is not a function. Next up is the vertical line test. If a vertical line passes through more than one point on a graph of a relation, then the relation is not a function. So just a couple of examples. Let's do an example of a graph that would pass the vertical line test. So we know this one. This is a parabola. All right. So if we drew a vertical line somewhere here, it would only cross the graph once in any given point that we crossed. It's only going to cross one point at a time. So that is a function. And then let's do an example of something that would not be a function. So, we can just do any graph we want. And so if we drew a vertical line here, that's going to cross in actually 3 points, so this would be not a function. So here we have 3 more examples, so take a quick second and determine whether or not they represent functions. Keep in mind the vertical line test says if it crosses more than one point, it's not a function. So for example A, we can draw a number of vertical lines here that will cause this to fail. So this is not a function. In B, no matter where we draw our vertical line, we draw one here, we draw one here, here, it's going to pass. It's only going to cross once, so this is a function. And then here, we look through, we're good for the first few points, but then here at the end, I can't really draw straight lines. It crosses these 2 points, so this is not a function. A function rule is an equation that represents an output value in terms of an input value. Commonly, we just know these as equations. So y equals 3x plus 2, where y is your output, x is your input, is a function rule. To be more fancy with it, you can change it into function notation where you're replacing your output with, and in this case, y, we're replacing with f of x. So in this case, function notation would be f of x equals 3x plus 2, where our output value, the y, has been changed into function notation, saying that f of x, or function f of x. So this function is a representation of x, or is in relation to x as its input. And then down here, we're helping you remember. Independent variable is x. It's the input of your function. Dependent variable, in this case, would be f of x or y, or the output of your function. So here in this example, it says f of x equals negative 2x plus 5. What is the output for the inputs of negative 3, 0, and 1/4? So we're just going to go ahead and evaluate this essentially 3 times. So f of negative 3 means we're going to plug in negative 3 for x. And we're going to see what we get. Negative 3 times negative 2 is 6, plus 5 is 11. So one of our outputs is 11. F of 0, so negative 2 times 0 plus 5. 2 times 0 is 0, plus 5 is 5. And then f of 1/4 equals negative 2 times 1/4 plus 5. Negative 2 times 1/4 is a negative 1/2. Negative 1/2 plus 5 is going to give us a positive, we can say 4.5 or 4.5. So these represent your outputs. And then example B here, for f of x equals negative 4x plus 1, what is the output for the given input? So for this, if we're looking at negative 2, we'd have f of negative 2 equals negative 4 times negative 2 plus 1. That's negative 4 times negative 2 is positive 8. 8 plus 1 is 9. And then for 0, so f of 0 equals negative 4 times 0 plus 1. So in this case, negative 4 times 0 is 0, plus 1 is 1. And then last but not least, f of 5 equals negative 4 times 5 plus 1. Negative 4 times 5 is negative 20. Negative 20 plus 1 is negative 19. And so your outputs in this case would be 9, 1, and negative 19.